Firstly, calculate the branch circuit loads. The walk-in coolers draw 2 times 30 amps, which equals 60 amps. The compressor fans draw 3 times 20 amps, which equals 60 amps. The outside lights draw 20 amps. The block heaters draw 2 times 20 amps, which equals 40 amps. Next, determine the feeder load. The lighting and receptacle load are 20 amps plus 40 amps, equaling 60 amps. The motor load, which is continuous, is 60 amps. The total feeder load is calculated to be 120 amps. The fuse rating is 100 amps. Since the total feeder load of 120 amps exceeds the fuse rating of 100 amps, the feeder is overloaded. The motors are rated for 208 to 230 volts, but are operating at 200 volts. This voltage drop can result in reduced motor performance and increased current draw. To resolve the overload condition and address the voltage issue, the following actions should be considered. 1. Upgrade the feeder. Increase the feeder size to number 1 copper and install a 125 amp fuse to accommodate the actual load. 2. Increase the voltage. Investigate and correct the cause of the voltage drop to ensure that motors are operating at their proper rated voltage. 3. Replace motors. If the voltage issue cannot be resolved, consider replacing the motors with ones rated for 120/208 volts. Additional considerations include ensuring that the branch circuits for the compressor fans and outside lights are protected with appropriate circuit breakers or fuses. The block heater should be wired in a manner that prevents them from being energized simultaneously. The NEC, or National Electrical Code, provides guidelines for conductor ampacity based on insulation type and installation method. For example, conductors with THHN insulation in a dry location can handle higher temperatures and thus potentially carry more current than conductors with lower temperature ratings. However, the ampacity must also be derated if multiple current-carrying conductors are bundled together in a conduit, as this reduces their ability to dissipate heat. The NEC specifies derating factors in Table 310.15 current. For instance, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. Voltage drop is another critical factor in electrical system design. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the impedance of the conductor in ohms per foot divided by 1000. Impedance values for different conductor sizes and materials can be found in NEC Chapter 9, Table 8. For example, suppose you have a 200-foot run of number 2 copper wire carrying 80 amps. The impedance of number 2 copper wire is approximately 0.194 ohms per 1000 feet. Plugging these values into the formula, we get voltage drop equals 2 times 200 times 80 times 0.194 divided by 1000, which equals 6.208 volts. If the source voltage is 240 volts, the voltage at the load would be 240 volts minus 6.208 volts, which equals 233.792 volts. In this case, the voltage drop is 2.59%, which is within the recommended limit. However, if the current were higher or the conductor length were longer, the voltage drop could exceed the limit, requiring a larger conductor size. Overcurrent protection is essential for preventing damage to electrical equipment and reducing the risk of fire. Circuit breakers and fuses are the two main types of overcurrent protection devices. Circuit breakers are resettable devices that trip when the current exceeds their rating, while fuses are one-time devices that melt and interrupt the circuit. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes in Table 310.16. For example, number 12 copper wire with THHN insulation has an ampacity of 30 amps, but it is typically protected by a 20 amp circuit breaker or fuse due to termination temperature limitations. The selection of overcurrent protection devices should also consider the type of load being served. For example, motor circuits require time delay fuses or inverse time circuit breakers to allow for the high inrush current that occurs when the motor starts. Grounding and bonding are critical for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which allows the overcurrent protection device to trip and clear the faults. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. The NEC specifies the requirements for grounding and bonding in Article 250. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding jumpers. For example, the grounding electrode system must consist of a metal underground water pipe, a ground ring, or rod and pipe electrodes. The equipment grounding conductor must be sized according to NEC Table 250.122 based on the rating of the overcurrent protection device. In the case of the walk-in coolers, each 30 amp compressor should have its own dedicated branch circuit. This ensures that a fault in one compressor does not affect the operation of the other. The branch circuit should be wired with number 10 copper wire and protected by 30 amp circuit breakers. The compressor fan motors, each drawing 20 amps, also require dedicated branch circuits. These circuits should be wired with number 12 copper wire and protected by 20 amp circuit breakers. The outside lights, with a total load of 20 amps, can be served by a single branch circuit. This circuit should be wired with number 12 copper wire and protected by a 20 amp circuit breaker. The block heaters, with a combined load of 40 amps, can be served by two 20 amp branch circuits. Each circuit should be wired with number 12 copper wire and protected by a 20 amp circuit breaker. However, it is important to ensure that the block heaters cannot be energized simultaneously, as this would overload the feeder. This can be achieved by using a control system that prevents both heaters from operating at the same time, or by installing a load management system. To address the voltage drop issue, several steps can be taken. 1. Check the voltage at the service entrance to ensure that it is within the acceptable range. If the voltage is low at the service entrance, contact the utility company to investigate the issue. 2. Inspect the connections at the service entrance, panel board, and equipment to ensure that they are tight and free of corrosion. Loose or corroded connections can cause voltage drop and overheating. 3. Use a larger conductor size to reduce the voltage drop. For example, upgrading from number 2 copper wire to number 1 copper wire will reduce the voltage drop by approximately 20%. 4. Shorten the length of the conductor run to reduce the voltage drop. If possible, move the panel board closer to the equipment. 5. Use a step-up transformer to boost the voltage at the equipment. This is a more expensive option, but it may be necessary if the voltage drop is severe. The feeder size is determined by the total load it is expected to carry. The NEC specifies the minimum feeder size in Article 220. The feeder must be sized to carry the non-continuous load plus 125% of the continuous load. In this case, the non-continuous load is 60 amps and the continuous load is 60 amps. Therefore, the feeder must be sized to carry 60 amps plus 1.25 times 60 amps, which equals 135 amps. Number 1 copper wire with THHN insulation has an ampacity of 150 amps, which is sufficient for this application. Therefore, upgrading the feeder to number 1 copper wire and installing a 125 amp fuse is a reasonable solution to the overload condition. However, it is important to verify that the existing panel board is rated for 125 amps and that the conductors are properly terminated. If the panel board is not rated for 125 amps, it will need to be replaced. It's important to note that motors typically draw significantly higher current when starting compared to their running current. This inrush current, also known as locked rotor current, can be several times the motor's full load amps. The duration of the inrush current is usually short, lasting only a few seconds, but it can still cause voltage dips and potentially trip circuit breakers or fuses if the electrical system is not properly sized. The NEC addresses motor starting requirements in Article 430, which provides guidance on selecting overcurrent protection devices and conductor sizes to accommodate motor starting currents. For example, the code allows for the use of time delay fuses or inverse time circuit breakers, which are designed to withstand short duration overloads without tripping. When sizing conductors for motor circuits, the NEC requires that the conductors have an ampacity of at least 125% of the motor's full load amps. This ensures that the conductors can handle the continuous current drawn by the motor during normal operation. Additionally, the code specifies different rules for sizing conductors based on the type of motor and its application. For example, conductors for motors used for intermittent duty, such as elevators or cranes, may be sized differently than conductors for motors used for continuous duty, such as pumps or fans. Overcurrent protection for motor circuits is designed to protect the motor and the conductors from overloads and short circuits. The NEC allows for the use of fuses, circuit breakers, or motor overload relays for overcurrent protection. The size of the overcurrent protection device is typically based on the motor's full load amps and the type of protection device being used. For example, the code allows for the use of fuses sized at up to 175% of the motor's full load amps for certain types of motors. Motor overload relays are designed to protect the motor from overheating due to prolonged overloads. These relays typically consist of a thermal element that is heated by the motor current. When the motor current exceeds a certain level for a certain amount of time, the thermal element will trip the relay, disconnecting power to the motor. Motor control centers, or MCCs, are commonly used in industrial and commercial facilities to house and control multiple motor starters and related equipment. MCC provide a centralized location for motor control, protection, and monitoring, making it easier to manage and maintain the electrical system. MCC typically include features such as motor starters, circuit breakers, fuses, overload relays, and control transformers. They may also include communication modules that allow for remote monitoring and control of the motors. When selecting an MCC, it is important to consider the size and type of motors being controlled, the environmental conditions, and the level of protection required. The MCC must be sized to accommodate the total load of all the motors being controlled, and it must be designed to withstand the environmental conditions in which it will be installed. Additionally, the MCC must provide adequate protection for the motors and the electrical system, including overcurrent protection, overload protection, and short-circuit protection. Variable frequency drives, or VFDs, are electronic devices that control the speed of AC motors by varying the frequency and voltage supplied to the motor. VFD offer several advantages over traditional motor control methods, including energy savings, improved process control, and reduced mechanical stress on the motor and driven equipment. VFD can be used in a wide range of applications, including pumps, fans, compressors, and conveyors. When selecting a VFD, it is important to consider the size and type of motor being controlled, the desired speed range, and the application requirements. The VFD must be sized to match the motor's voltage, current, and horsepower ratings. Additionally, the VFD must be programmed to operate the motor at the desired speed and to provide the necessary protection features. Harmonic distortion is a phenomenon that occurs in electrical systems when nonlinear loads, such as VFD, computers, and electronic lighting ballasts, draw current in a non-sinusoidal manner. These nonlinear currents create harmonic voltages and currents that can propagate throughout the electrical system, causing a variety of problems. Harmonic distortion can lead to overheating of transformers and conductors, misoperation of protective devices, and interference with sensitive electronic equipment. To mitigate harmonic distortion, several techniques can be used, including the use of harmonic filters, line reactors, and isolation transformers. Harmonic filters are designed to block harmonic currents from flowing into the electrical system. Line reactors are used to reduce the amplitude of harmonic currents. Isolation transformers are used to isolate sensitive equipment from harmonic voltages and currents. Power factor correction is the process of improving the power factor of an electrical system. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction can be achieved by adding capacitors to the electrical system. Capacitors store electrical energy and release it back into the system, which reduces the amount of reactive power that must be supplied by the utility. Improving the power factor can reduce energy costs, improve voltage regulation, and increase the capacity of the electrical system. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power line switching, and other transient events. Voltage surges can damage or destroy sensitive electronic equipment, leading to costly repairs and downtime. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. SPD are typically installed at the service entrance, panel boards, and individual equipment locations. When selecting an SPD, it is important to consider the surge current rating, the voltage protection level, and the application requirements. The surge current rating indicates the maximum surge current that the SPD can withstand. The voltage protection level indicates the maximum voltage that the SPD will allow it to pass through to the protected equipment. Lighting protection systems are designed to protect buildings and other structures from lightning strikes. A lighting protection system typically consists of air terminals, conductors, and grounding electrodes. Air terminals are installed in the roof of the building and are designed to intercept lightning strikes. Conductors are used to carry the lightning current from the air terminals to the grounding electrodes. Grounding electrodes are buried in the earth and are used to dissipate the lightning current safely into the ground. The design and installation of lighting protection systems must comply with the requirements of NFPA 780 standard for the installation of lighting protection systems. Electrical safety is paramount when working with electrical systems. It is essential to follow safe work practices and to use appropriate personal protective equipment, or PPE. Safe work practices include energizing electrical equipment before working on it, using lockout/tagout procedures to prevent accidental energization, and maintaining a safe working distance from energized parts. PPE includes items such as insulated gloves, safety glasses, and arc-rated clothing. The selection and use of PPE must comply with the requirements of OSHA 29 CFR 1910.132-137. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault creates an arc of electrical energy. Arc flash events can generate intense heat, pressure, and light, causing serious burns, injuries, and even death. To protect workers from arc flash hazards, it is important to conduct an arc flash hazard analysis to determine the potential arc flash energy levels at different locations in the electrical system. Based on the results of the arc flash hazard analysis, appropriate PPE must be selected and used. The requirements for arc flash hazard analysis and PPE are specified in NFPA 70 standard for electrical safety in the workplace. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the hot and neutral conductors, it indicates that current is leaking to ground, which could be a sign of an electrical shock hazard. GFCIs will trip the circuit when a ground fault is detected, interrupting the flow of electricity and preventing electric shock. GFCIs are required in many locations by the NEC, including bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or ASIs, are designed to protect against electrical fires. ASIs monitor the current flowing in a circuit for the presence of arc faults, which are small, unintentional electrical arcs that can generate heat and ignite nearby materials. ASIs will trip the circuit when an arc fault is detected, interrupting the flow of electricity and preventing a fire. ASIs are required in many locations by the NEC, including bedrooms and living rooms. Electrical inspections are an important part of ensuring the safety and reliability of electrical systems. Electrical inspections are typically conducted by qualified electrical inspectors who are trained to identify electrical hazards and code violations. Electrical inspections may be required for new construction, renovations, and additions. The electrical inspector will review the electrical plans, inspect the electrical installation, and issue a report of any deficiencies. It is important to correct any deficiencies identified by the electrical inspector to ensure that the electrical system is safe and compliant with the NEC. Proper grounding and bonding are absolutely critical for electrical safety. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. The NEC specifies detailed requirements for grounding and bonding in Article 250. Grounding electrode systems must consist of a metal underground water pipe, a ground ring, or rod and pipe electrodes. Equipment grounding conductors must be sized according to NEC Table 250.122 based on the rating of the overcurrent protection device. Bonding jumpers must be used to connect metal parts of the electrical system together, such as metal conduits, enclosures, and equipment. Regular maintenance of electrical systems is essential for ensuring their continued safety and reliability. Electrical maintenance includes tasks such as inspecting and testing electrical equipment, tightening connections, cleaning components, and replacing worn or damaged parts. Regular maintenance can help to prevent electrical failures, reduce downtime, and extend the life of electrical equipment. A qualified electrician should perform electrical maintenance. They have the knowledge, skills, and tools necessary to safely and effectively maintain electrical systems. They can identify potential problems before they cause failures and can perform repairs and replacements as needed. Electrical drawings and diagrams are essential tools for designing, installing, and maintaining electrical systems. The electrical drawings show the physical layout of the electrical system, including the location of equipment, conduits, and wiring. Electrical diagrams show the electrical connections between different components of the system. Electrical drawings and diagrams are used by electricians, engineers, and other professionals to understand the electrical system, troubleshoot problems, and make modifications. The NEC requires that electrical drawings and diagrams be provided for many types of electrical installations. These drawings and diagrams must be accurate, complete, and up-to-date. They must also be readily accessible to those who need them. Troubleshooting electrical problems can be challenging, but it is essential for maintaining the safety and reliability of electrical systems. Electrical troubleshooting involves identifying the cause of an electrical problem and taking corrective action. Electrical troubleshooting typically involves using test equipment such as multimeters, clamp-on ammeters, and insulation testers. It also involves using electrical drawings and diagrams to understand the electrical system. A qualified electrician should perform electrical troubleshooting. They have the knowledge, skills, and tools necessary to safely and effectively troubleshoot electrical problems. They can identify potential hazards and can take appropriate precautions to prevent injury. Electrical codes and standards are essential for ensuring the safety and reliability of electrical systems. Electrical codes and standards provide requirements for the design, installation, and maintenance of electrical systems. The NEC is the most widely adopted electrical code in the United States. It is updated every 3 years by the National Fire Protection Association, or NFPA. The electrical codes and standards are developed by experts in the electrical industry. They are based on the latest research, technology, and best practices. Compliance with electrical codes and standards is essential for ensuring the safety of people and property. Electrical education and training are essential for anyone who works with electrical systems. Electrical education and training provides the knowledge and skills necessary to safely and effectively install, maintain, and troubleshoot electrical systems. Electrical education and training is available from a variety of sources, including trade schools, community colleges, and universities. Electrical education and training programs typically cover topics such as electrical theory, electrical codes and standards, electrical safety, and electrical troubleshooting. Completion of an electrical education and training program can lead to certification or licensure as an electrician.